Materials as a computational system, from pictures to physics and parametric design. Introduction. Why materials are the weakest link in digital design. For decades, digital design tools have focused on geometry. Surfaces, curves, solids, assemblies, all increasingly precise, parametric, and expressive. Yet, despite this progress, one fundamental aspect of manufacturing has remained surprisingly passive: material. In most CAD systems, material is treated as a visual attribute or a descriptive label. It defines color, texture, or appearance in rendering, and later appears as a textual entry in a bill of materials. But it rarely participates in the logic that generates the geometry itself. This separation creates a familiar and costly problem. Designs look correct on screen, pass internal reviews, and even receive commercial approval, only to fail when they reach production. The reason is simple. Geometry was designed independently of the physical constraints imposed by material reality. The passive material problem. In traditional workflows, material is applied after geometry is defined. A designer models a product assuming a nominal thickness, flexibility, or machining method. Later, the material is changed for availability, cost, or specification reasons. Consider a simple example. A furniture component is designed using plywood with a thickness of 15 millimeters. Joints, grooves, and tolerances are modeled accordingly. Later, the specification changes to plywood of 18 millimeters. In most CAD systems, the material label updates, the BOM entry changes, but the geometry remains exactly the same. As a result, joints no longer fit, clearances are violated, assembly logic breaks. The model becomes invalid, not visually but physically. This is not a user error, it is a structural limitation of systems where materials are passive. Parametric design without physical logic is incomplete. Parametric design is often presented as a solution to flexibility. Change a parameter, and the model updates automatically. But when materials are excluded from the parametric logic, this flexibility remains superficial. Geometry adapts, physics does not. The result is a paradox. Designs are parametric, but manufacturing constraints are static. This is where many parametric systems fail to scale in real production environments. The BeeGraphy perspective. Material as an active computational entity. BeeGraphy approaches material from a fundamentally different angle. In this paradigm, material is not an attribute, it is a computational entity. A material does not decorate geometry, it informs geometry. Instead of being applied after modeling, material participates directly in the logic that generates the design. In practical terms, the material dictates the rules under which geometry is allowed to exist. The 4 layers of material logic. To understand how this works, material must be decomposed into structured layers of logic. 1. Geometric constraints. Every material introduces hard geometric limits. Thickness determines joint dimensions, offsets, minimum feature sizes. Sheet size determines maximum part dimensions, segmentation logic, assembly strategies. In a computational system, these values are not referenced manually. They are constraints that shape geometry automatically. Change the thickness, and every dependent dimension recalculates. 2. Physical properties. Materials carry physical behavior. Density influences weight. Grain direction influences strength and cutting orientation. Rigidity influences allowable spans and tolerances. When these properties are formalized, they affect nesting orientation, structural logic, machining feasibility. Design decisions stop being aesthetic guesses and become physical responses. 3. Processing rules. Materials cannot be separated from the way they are processed. Different materials imply different cutting speeds, different tool constraints, different allowable operations. In a computational system, these are not stored as instructions. They are rules. If a material does not allow a certain operation, the geometry that requires it cannot exist. 4. Economic logic. Material choice always carries economic consequences. Price may be calculated per square meter, per sheet, per linear meter, or per unit weight. Processing time, waste, and tooling all influence cost. When economic logic is embedded in the material definition, pricing becomes a derived result, not a manual calculation. Active behavior. What happens when material changes? The true power of computational materials becomes visible when material is switched. Consider this scenario. A design initially uses MDF 16 millimeters. The user switches to solid wood 25 millimeters. In a traditional system, this would require manual geometry edits, engineering review, revalidation. In a computational material system, groove widths update automatically, joint geometry adapts, nesting orientation changes to respect grain direction, processing time recalculates, cost updates accordingly. The design remains valid. By construction, no reinterpretation, no redesign. Designing within reality, not after it. This approach fundamentally changes the nature of digital design. Design is no longer an abstract exercise that hopes to survive contact with reality. It becomes an act of reasoning within the boundaries of physical constraints. The question shifts from, can we manufacture this, to, what is the best possible design that obeys these constraints? This eliminates one of the most dangerous moments in manufacturing. We designed it, but we can't build it. Why this matters for industry. For manufacturers, the implications are significant. Fewer errors at handoff, fewer redesign cycles, higher confidence in customization, better alignment between design, pricing, and production. Most importantly, engineering knowledge becomes embedded in the system rather than residing in individual experts. This is not automation for efficiency alone, it is formalization of physical knowledge. Conclusion. From pictures to physics. When materials are treated as textures, design remains superficial. When materials are treated as constraints, design becomes engineering. BeeGraphy's approach demonstrates how parametric systems can move beyond visual flexibility and into physical validity. This shift, from pictures to physics, is what separates geometric software from true computational manufacturing systems. In such systems, reality is not checked at the end. It is encoded at the beginning. And when design obeys reality by default, manufacturing stops being a risk and becomes a computation.